first logistical thing is our exam 2, midterm 2 is next Thursday, okay? During class time, same as exam 1. What did we study last week? What did we learn last week? Power, work, and energy for a particle. So what is the power of a force, F, acting on a particle of mass m velocity v? What is the power of a force by definition? F dot v. Okay, what's the work of a force? Integral of F dot v dt, right? Or the integral of F dot dr. So that's a line integral. Okay, then what? What's the kinetic energy of a particle? Half m v dot v. And then what's the work energy theorem for a particle? What does it say? What does the work energy theorem for a particle say? Right, so the change in kinetic energy for a particle is equal to the work of the forces acting on it. Okay? So I need someone from here to answer now. When is the energy of a system conserved? So this group here, when is the energy of a particle conserved? What do we think? When is the energy of a particle conserved? Well, maybe let me ask an easier question first. We can divide forces into conservative and non-conservative forces. What's the difference between a conservative force and a non-conservative force? Yes?
The force is constant.
What do you mean? A conservative force is constant? What do we think? What's the difference between a conservative force and a non-conservative force?
The conservative force has a formula that it follows, a gradient.
So does the work of a conservative force depend on the path traveled by the particle? No. It only depends on the endpoints, right? And we learned about 3 types of conservative forces. What are they? Any constant force is conservative, which includes the weight force. So any constant force is conservative, but not all. But conservative forces is not the same as constant forces, right? Okay, what other conservative force do we know of? Spring force is conservative. What else? The gravitational force. Okay, so then if all the forces that are doing work on a system are conservative, what can we say about the energy of a system? That it's conserved, right? Could we have a system with, for example, a normal force acting on it, and the energy of the system still be conserved? Yes. But what would need to happen here? Yes.
It returns to the same point.
Not quite. So I have a system, I have a non-conservative force acting on it, for example, the normal force. Is it possible for the energy of the system to be conserved? Yes, the normal force needs to be workless, right? So if all the non-conservative forces are workless, the only forces doing work on the system are conservative, then the energy of a system is conserved, okay? Okay, great. So that's the work energy theorem for a particle. Then what did we talk about on Thursday? Oh, still on Tuesday and Thursday. What else did we discuss? Momentum. Okay, we have 2 types of momentum. What are they? Linear momentum and angular momentum. So linear momentum, we already know the balance of linear momentum, right? F is equal to g dot, or F equals ma. What new did we learn there about the balance of linear momentum? What is it? Exactly, the linear impulse linear momentum equation, which is obtained how? By taking the integral of the balance of linear momentum with respect to what? time, exactly. So we have the linear impulse, linear momentum equation, and then we introduced angular momentum. How is the angular momentum of a particle defined? Moment of linear momentum. So the angular momentum of a particle about a point O is r cross mv. R cross mv. About any point P is r minus rp cross mv. Okay, so that's angular momentum. Then we have the balance of angular momentum. Sum of moments about point O, a fixed point O is equal to the rate of change of angular momentum h dot O. Okay. Then we talked about what? Collisions, right? Collisions. So if I have two particles in the plane that are colliding, what conservations do I have here? What kind of momentum? Linear or angular?
Linear.
For which system?
Cartesian.
What is it? For which system? Was it like M1, M2, or both?
Both.
Okay, so your friend is saying I have conservation of linear momentum. So raise your hand if you agree with this. So the linear momentum of M1 and M2 is conserved during collisions. Okay. Why? Why is it conserved during collisions? During the collision? How do we know if the linear momentum of a system is conserved?
Such a short time.
There's no net force acting.
Exactly. So if f is equal to 0, then in the linear impulse linear momentum equation, if the integral of fdt is equal to 0, then the linear momentum is conserved, which is true here. All the forces acting on this system that are external to the system, because the impact forces here cancel out. So all the external forces acting on the system, they're either zero, or they're smooth. So their impulse over the very short interval of impact is going to be 0. Any other conservations? Yes.
Each of the two particles has conservation of linear momentum in the tangent direction.
Exactly. Why?
Because there's no force in the tangent direction.
Exactly. All the impact forces are along the normal. So where the two particles meet, we can define a normal direction, a tangent direction, and we can say that linear momentum Okay, so it seems like we have a lot of studying to do, right? So that's up to set 13 that we should have covered so far. You'll do some problems about collisions and angular momentum in the exercise session tomorrow. Today we're covering systems of particles, and then on Thursday we'll start with rigid bodies. We might start today if we finish systems of particles quickly. Okay, so we're going by fast. I want you all to review everything and solve all the problem sets. If you have any questions, let us know. Any questions about anything we covered today so far, like our quick review? Questions? Okay then, systems of particles. So everything we studied for one particle, the kinematics, position, velocity, acceleration, all the balance laws, balance of linear momentum, balance of angular momentum, work energy theorem, all of these that we covered for one particle, right now we're going to cover for a system of particles, and then later on we're going to cover them again for a rigid body. So this is our progression here. Okay. Okay. So we're considering a system of n particles. So particle 1, 2 through n. Okay. So the mass of each particle is m1, m2 through n. And for a typical particle mi, I can draw its position vector ri. Okay, so again, we have a system of n particles. For a typical particle, I can write its mass mi. Its position vector for a typical particle called I. So I'm listing all the kinematical quantities for a particle. So I have the mass, position, velocity, acceleration, linear momentum, angular momentum, and kinetic energy. What is the angular momentum of a particle about the point P? About point P, not the origin. So what is it going to be? The angular momentum of a particle about the point P. Exactly. Ri minus Rp plus mi vi. Okay, what else do we have left? Kinetic energy. What's the kinetic energy of a particle? Mass mi, velocity vector vi. Right. Okay, so these are the kinematics. Then we have the kinetics. Any questions so far? Questions? Okay, what are the balance laws for a particle? The balance of linear momentum. What else? The balance of angular momentum. Plus the time integrals of these, so the linear impulse linear momentum equation, angular impulse angular momentum equations. Okay. What else do we have as Balance law?
Conservation of energy.
The work energy theorem. Okay. Okay. So this is kind of a summary of a lot of what we've learned about a particle since the beginning of the semester. Now we want to find what all of these quantities are for a system of particles. Any questions about any of what's written on the board? Any questions at all? Okay. So for a system of particles, let us start with the kinematics. Kinematics. How do you think I would define the mass of this system of particles, the total mass of this system? That's going to be equal to what? The sum of the individual masses of all the particles, right? And total is equal to the sum I equals 1 to n of mi. Raise your hand if you're familiar with this notation. Great. What does it mean? Yes?
You're going through the list of all the n's that you think of together.
Exactly. So I go from 1 to n, so 1, 2, 3 through n. And for each I, I'm going to sum mi. So basically that's going to be m1, m2, m1 plus m2 through mn. So this is a shorthand for this. Any questions? Okay. How will I define the position vector? Position vector of the system. What do you think? We might introduce a new quantity here that maybe you're familiar with, or you should be familiar with from statics, yes.
Is it like a weighted average of all the
Exactly. And what is that called?
center mass?
Exactly. So we're going to introduce the center of mass for a system of particles, and we're going to write the position vector of the center of mass. And as your friend mentioned, the position vector to the center of mass is the weighted average of the position vectors of all the particles. But what is it weighted by? The mass. Exactly. Exactly. So if I have a particle of mass m here, 2m there, the center of mass is going to be closer to here or to there? To there, to the heavier particle. Position vector the center of mass, I'm going to call it C. The position vector to C is going to be the sum of mi, the position vectors of each particle over the sum of mi, total mass. Okay, so take a minute with your neighbor, calculate the position vector of the center of mass of this system. What is RC? Okay, so just you need a minute to do that. Okay. Do you find the center of mass? Okay, this should take us a minute. We need to be quick, quick, quick. How do you what?
Combine the R vectors.
What do you mean combine them?
You just add them up, right?
What does combine mean? Raise your hand if you're done. Let me see. Okay, so if you're done, my question to you is the center of mass on the line connecting 1 and 2? Yes or no, and then how can you show it? Right. So RC is equal to what? Who can help me? How do I calculate the position vector of the center of mass here?
13
Mm-hmm.
fourths EX.
You need to help me get to that answer.
So for the EX, the EX component, you have 4EX times 3M for R2, and then you have 1EX times 1M.
Right, so I'm using that equation, okay? And I'm summing the mass of particle 1 times its position vector, which is mR1 plus 3m R2 over the total mass, which is m plus 3m. So these m's cancel out. I'm left with a 1 over 4 of R1, which is EX plus EY, plus R2, which is plus 4EX. So this becomes a 5 over 4 EX plus 1 over 4 EY.
Where's that 3? Where did 3 go?
Oh, we forgot the 3. So that's a 3 times, so that's a 12. Yeah.
That's on the EX.
Does this look good? Okay, great. Any questions about this? Okay, so the center of mass, by intuition, we know it's going to be somewhere along the line connecting M1 and M2, probably closer to M2. So 13 over 4, that's so 3 point something, 3.25 EX plus 1 over 4 EY. I can actually define if I wanted to, I could define a new basis. u v. And I could say that, call this location A, this location B. RC with respect to A is equal to M1 R1 with respect to A, which is M2 R2 with respect to A, over M1 plus M2. So now I'm calculating the center of mass, but I'm calculating it taking a new origin, which is what? A. Okay? So if A is my origin, particle 1 is at the origin, so this position vector is what? 0. Okay, M2 is the same, 3M. What is R2? R2, I can write it as whatever this length is along U. L is just the magnitude of R2 minus R1 over M1 plus M2, which is M plus 3M. So then we can show pretty easily from there that C is indeed located along the line joining M1 and M2. Another way to show this would be to actually get the equation of the line joining M1 and M2 on the xy basis, ex, ey, and then check that C belongs to that line. Any questions?
This only applies to a two-particle
Yeah.
system.
If you have more than two particles and they're not collinear, the center of mass is going to be located somewhere in between. But here I want to add this equation that I use that you can show from this one. Just by subtracting. So you can show this equation, but this one just by subtracting RA, both sides of the equation. Any questions? Yes.
When would we use the reference point?
There might be times where it's convenient to calculate the center of mass, not relative to an origin, but relative to some other point. So for example, if I have a dumbbell that is moving in space, the center of mass is going to move in space too, right? As this dumbbell moves in space, the center of mass moves in space, right? But for me, it might be convenient sometimes to calculate the distance between C and one of the edges of the dumbbell, which is a constant distance, right? So in this case, I would rather use this equation. We'll see examples. We'll see examples of this. Yes?
Is A one of the points in the system?
Doesn't have to be. It's just, you can think of it as a new origin. So I can actually obtain this equation from this one by just subtracting RA, where RA could be the position vector of any point. Good questions. Any other questions? Questions. Okay. So let us see, what have we done so far? The mass of the system, the position vector of the system. Now the velocity of the system, that's going to be the velocity vector of the center of mass, which is going to be what? Can anyone guess? How do I find the velocity of the center of mass of a system of particles? Yeah, I'll take the time derivative of the position vector of the center of mass. So I can either calculate the center of mass and then take its derivative, or I can calculate the sum of mi vi over the sum of mi. Same for the acceleration. Any questions so far? What is next on our list? The linear momentum. Okay, so the linear momentum for a system of particles is defined to be the sum of the linear momentum of each constituent. What does SOP stand for? System of particles. Constituents. So the linear momentum of a system of particles is the sum of the linear momentum of the individual particles. Exactly. Where the linear momentum of each particle, this I can write as the sum of mi vi. And but your friend is noticing that the sum of mi vi, from here, I can write as what? The sum of mi vi? Total mass times Vc. Is the total mass times Vc. So then if we want to calculate the linear momentum of a system of particles, that would be equivalent to calculating the linear momentum of one particle whose mass is the total mass of the system and its velocity is the velocity of the center of mass of the system. Kind of gives you an intuition that for a system there exists an equivalent particle for the purpose of calculating the linear momentum, where the linear momentum of the equivalent particle is the same as the linear momentum of the system. And that's actually a concept that's used in multiple dimensions. Like for a rigid body, how many degrees of freedom does a rigid body have? 6, right? 3 translational, 3 rotational degrees of freedom. We can define a superparticle, which is a particle that is equivalent to a rigid body that moves in 6 dimensions. For a system of particles and rigid bodies, we can do the same. You would learn about that in the intermediate dynamics course, ME 175. But for now, just a way to remember that the linear momentum of a system of particles is the sum of the linear momentum of the individual particles, which is equivalent to the total mass of the system times the velocity of its center of mass. Now, angular momentum. Any questions? Angular momentum is the same too. So the angular momentum of a system of particles about point P is equal to what? The sum of Ri minus Rp cross MIVI for each particle. Okay. Okay. So the angular momentum of a system of particles about point P is the sum of the angular momentum of each particle about P, which is this, right? Which we can equivalently write as this. We need to show this. But before we show this, what is HC here? The angular momentum of a system about C, the center of mass. What would that be equal to? Exactly. I just replaced point P by the specific point C, the center of mass here. So that would be Ri, so the sum of Ri minus Rc cross MIVI. Okay. So how do you think I will show how to get from this to this expression, or to show that these two expressions are equivalent? What do I do? Any ideas? Maybe take a minute, chat with your neighbors, let me know if you have any ideas. I want to show that these two forms of HP are equivalent. Okay. Any ideas? I'm going to use a trick here, which is starting with this expression. HP is equal to the sum of Ri minus Rp cross MIVI. I will add here plus Rc minus Rc. So I've maintained the equality, right? I've added a number or a vector, and I've subtracted the same vector. So I've maintained the equality. So then what I can do is I can split the sum, right? I can split the sum into the sum of Ri minus Rc cross MIVI plus the sum of Rc minus Rp cross MIVI. Make sure your neighbor is okay with this step. If you have any questions, let me know. Splitting the sum. And you can replace the vectors with numbers. If I have the sum of 2 plus 3x, I can say that that's equal to the sum of 2x plus the sum of 3x. I equals 1 to 3 or whatever. Maybe a bad analogy, but any questions? Questions? Okay. What is this first sum equal to? HC. This is equal to HC. Now what about this one? It should be equal to what? That one, right? Okay. Here, I'm summing RC minus RP cross MIVI. I'm summing over which index? I, right? I equals 1 to n. Does RC minus RP depend on I? No. So what can I do? I can pull it out of the sum. Kind of like an analogy to integrals. Or if I'm summing 2x, x equals 1 to 3, that's equal to 2. Summing x equals 1 to 3. So I can pull the constant outside the sum. So I'm going to do the same here. Plus so again, the summation index is I. This term here does not depend on I, right? Doesn't. So I can take it outside the sum. So I'm left with RC minus RP crossed with the sum of MIVI. What is the sum of MIVI? Yes, it is G. G. So now we've covered that HC is equal to RC minus RP plus G, which is the result that I wanted. Any questions? Questions?
You can also define HC with the cross G as well, right?
You can define, can you say again?
Like HC is RP minus RC, or RC.
Yes, that's a good point. So if I look at this expression here, HP is equal to HC plus RC minus RP plus G. If I replace P by C, what will I get here? HC is equal to HC plus RC minus RC plus G, which is 0. So that's HC is equal to HC. So my answer is consistent. Okay? Now I want you to do any questions? I want you to do a short 10-minute quiz which involves showing that HC can be written as so a very short 10-minute quiz to show this, that this is equal to this. So I'm setting the due date to 11:10, and you can work on this in pairs. Any questions?
I'm kind of stuck. I was able
Check with your neighbor. Any ideas? You will use the trick. You could use the trick we used in this previous derivation.
Thank you.
No.
I did the same
Can I
thing.
take a
did
look?
the same, like, something, yeah. So I separated it. Now I just have MI and VC on this side. While I do have the term that we want on the right side.
So you need to show that this is 0.
Yeah, I'm trying to prove that it's 0. I don't get. Yeah, that's the part I'm stuck.
Think about it. Is there some term you can take outside the sum because it doesn't depend on I?
Oh,
Think. Did I give you a sheet?
We had no. Yeah, because when we're adding RP, like there's a reason why, because it shows up in the equivalent state.
RC plus minus VC. RC. I mean, just like separate the sum.
With this thing. So you might want to do like V add VC and minus VC.
Yeah.
Because that's it.
Sum of RI minus RC cross MI VI. That's sum of RC minus.
I'll give you a bit of extra time. So. No, we can like start with this and show this.
Oh, sorry.
Or start with this and show this.
Oh, just so either way is fine. Or?
Yeah.
Oh, okay.
You want to show that they're equivalent.
Gotcha. Okay, so I guess I'll just go the other way.
It doesn't matter. Any questions? I hope auto complete doesn't help you solve it. Do it for you. You're welcome. Okay, cool. So one of these terms should be 0, and you get this, right? So this term should be 0.
Yeah.
How to show that it's 0?
is the after you do this, right? The RC or this one, this term doesn't really change, but
Wait, what is equal to what?
this.
I don't understand though. So this and this are equals. You can put an equal sign here because you added VC, you subtracted VC. But how come you can take the plus minus and then have a minus times? You can split this into two sums.
Into. I mean, two sums.
Like this is kind of you're summing like A times B plus C, which is equal to A times B plus A times C kind of thing. Yeah.
On the right track. I distributed each one.
I don't think this is gonna help. No. You're gonna wanna work on this part, right? Because this part is already the same between the two terms.
Oh, I want to work on this part.
Yeah, the velocities. You're welcome.
So we're at this point in time.
So, any updates?
So we're thinking of like splitting the sum for this one, right? But I don't.
No, you don't need to split the sum.
I don't need to split some for this
No.
one. Okay, yeah.
But you can take one term outside the sum. The term that does not depend
That
on
doesn't
I.
depend on- So it'll just be VC times the.
Right.
I work backwards from.
So you just do VC times RI.
No, you cannot switch the cross product.
Yeah, that's what I'm wondering.
So you can do the sum of MI or I minus RC parenthesis cross VC.
Oh, so you'll just cross it again? You're saying? Sorry, I'm a bit confused. So it would be like this? Is that what you're saying? So you'd print. Sorry, my handwriting's a bit off.
Yeah, you need to add.
Because the sum doesn't.
Yes,
Yeah.
but there's no cross MI because you cannot cross with the scalar. So that would be
Oh, no, just
the
times it.
scalar you can
You'll
switch.
just multiply by.
Yeah.
You just multiply by.
Split off the VC.
Okay,
Add
so-
VC,
Yeah.
subtract VC.
Yes. Then this term is 0.
Because.
Mm.
Okay, that's what I'm gonna figure out. Thank you.
Okay.
Yeah.
Oh, I did the plus minus
You
VC.
can split it to show it. Hmm?
I did the
I don't remember
plus
what it is.
VC minus VC,
Mm-hmm.
and then I split off the plus VC.
Yeah.
component.
So this term is 0.
Yeah, I'm trying to prove that this is 0.
Yeah. Take VC outside the sum
Oh, not true. Okay.
because it does not depend on I. Did you do this on your own? Yes. Can you explain it to your neighbors behind you? Mm-hmm.
I've gotten to here,
Mm-hmm.
and so I assume we have to prove this to be 0.
Yes.
Okay. Is that is the G relationship helpful or no? Just this.
I don't think so. So
Okay.
this is still MI over
Okay,
here.
okay.
Okay, but what you can do is you can take VC outside the sum. The cross VC, you can take it
Here.
outside the sum. So yeah,
So
you
is
cannot switch because it's a cross product. But you can say that that's parentheses, the sum of MI or I minus RC crossed with VC. Kind of like that. then this somehow you can show that it's equal to. Any questions?
It looks good.
Okay. I'm going to extend the deadline a little bit till 10:15. If you're done, you can take a small break. So I'm extending the deadline till 11:15. If you're done, you can take a small break. How do you show this is equal to 0? Why aren't you underlining vectors?
I'm trying to take out like the positive VC over here. Let me do this.
This you can take out by distributing the sum.
Distributing the sum. Oh.
Right. You have the sum of A cross B plus C, which is the sum of A cross B plus the sum of A cross C.
Oh, okay, gotcha.
Yeah, which is 0. The sum of MIRI minus the sum of MIRI is 0.
This is RC.
Oh, well, it's the sum of MIRI, which is going to be MRC, and then the sum of MIRC is also MRC. Because RC you can take out to the sum.
Oh, yeah, okay.
So from the definition of the center of mass, the sum of MIRC minus the sum of MIRI is 0. Yes.
I understand that you had to prove that this part equals 0. So I made RC equal to the definition of RC, and then can you just cancel these out to equal 0? But like, I don't really understand how it works with the sum.
Okay. Well, first of all, here you need to clarify that the cross VC is outside of the sum, so you need to put the big parentheses. Okay. I don't know how you can see from here. You can barely. Okay. Okay. So now we have the sum of MIRI minus the sum of MI, can take parentheses RC.
Okay.
Which, if you look at the definition of the center of mass,
Yeah.
the sum of MIRC minus the sum of MIRI is 0.
Wait, where?
The definition of the center of mass. So if you multiply the sum of MIRC times RC is equal to the sum of MIRI.
Yeah. Okay.
So this
then
gives you,
that-
yeah,
that's
these
what-
yeah.
that's the same.
Mm.
Okay.
Yeah, yes.
Have you seen the score for the game?
What game? Which game is going right now?
We'll just finish with Argentina versus Egypt.
Oh, Egypt, how much did they?
And Argentina was down 0-2, and then they went all the way back and 3-2 and won.
Oh, wow. Argentina was down 0-2 against
Yeah.
Egypt?
Yeah. And they were for almost the entire game, and they got like two goals in 5 minutes. It's crazy.
Oh, gosh.
It's going crazy.
Yeah, like it's Egypt's first time in the World Cup. And Argentina won last time.
Yeah, it's
Okay, are we done? Any questions? Questions? I was sad that you asked last, Lola. Yesterday. Okay, couple more minutes. Questions, as many questions. Are we all done? Okay. Okay, so the kinetic energy, again, it's the kinetic energy of a system of particles is defined to be the sum of the kinetic energies of the individual particles, which is the sum of half mi vi dot vi. And with the summary in front of you, equation 7, you can see that I can write this as half m vc dot vc plus half the sum of mi vi minus vc dotted with vi minus vc. Okay. Before we do this, one comment I want to make about this. Why is this term equal to 0? What does this term mean? This is a weighted average of the position vector of all the particles relative to the center of mass, right? So again, what is this term here mean, and why is it 0? That's the weighted average of the position vectors of each particle relative to the center of mass. So that's like calculating the center of mass, where my new origin is the center of mass itself. So where do I expect the center of mass to be if my origin is the center of mass? At itself, 0. So that's why this term is 0 kind of intuitively. I'm calculating the weighted average relative to the center of mass, which is going to be at the center of mass. Okay, now going back to the kinetic energy. The kinetic energy of a system of particles is the sum of the kinetic energies of the individual particles, which is amounts to this expression. So notice that the kinetic energy of a system of particles, is it equal to the kinetic energy of an equivalent particle of mass m and velocity vc? No. So I have half m vc dot vc plus a bunch of other terms. So I cannot use kind of the equivalent particle analogy for the kinetic energy. The kinetic energy of the system is not half the total mass times the velocity of the center of mass squared. No, there are extra terms, and I can show this. So if I start with half mi vi dot vi, using the trick that we just learned, I will introduce plus vc minus vc on both terms. So that's the sum of half mi vi minus vc dotted with vi minus, okay, no, I need to add, hold on, plus vc. Vi minus vc plus vc plus dotted with half, no. Okay, let's focus. That's going to be vi minus vc plus vc. Okay, and now I can divide this into this plus this plus this. So that's going to be a plus b squared. That's going to be a squared plus b squared plus 2ab. So that's equal to the sum of half mi vi minus vc dot vi minus vc plus half mi vc dot vc plus 2 times the sum of half mi vi minus vc divided with vc. Double check my work, let me know if I made any mistakes. One of these terms is going to cancel out, right? Which one? First, second, or last? Which one? The last one cancels out. Why? Exactly. It's the same reasoning as the here. I can take the center of mass outside the sum, and now that's basically the sum of mi vi minus the sum of mi vc, which is going back here, the sum of mi vi is equal to the sum of mi vc, so their difference is going to be 0. So this term is 0. 0 vector or 0 scalar? Okay, and then here I can take VC and VC outside. I'll have the sum of MI, which is MVC dot VC, and then this term is this. So I've shown what I needed to show. Any questions? Raise your hand if you're mostly okay with this. Yeah? Any questions, major concerns, anything? Redo these calculations at home, please, today. Okay. So where are we with our plan? Our master plan. Okay. So we had all of these quantities defined for a particle. Mass, position, vector, velocity, acceleration, linear momentum, angular momentum, kinetic energy. We defined them for a system of particles. So now we have to go to the kinetics so that we can start solving problems. So let's do that quickly. Okay, so I'll leave this here. Kinetics. Actually, I'll go here. And I'll erase this board. And left. Right, okay. So in our system of particles, a typical particle I, it's gonna have a resultant force Fi acting on it. So F1, F2 acting on particle 2, Fi on particle I, Fn on particle n. So the balance of linear momentum for a system of particles is going to be the sum of the balance of linear momentum for each individual particle. So balance of linear momentum is going to be the sum of Fi is going to be equal to the sum of G dot I. So summing the linear momentum for each particle, we're going to get the balance of linear momentum for the system. Okay, so the sum of all the forces acting on the system, I'm going to call that F. If we have any internal forces action-reaction forces from Newton's third law, they will cancel out. And how do I calculate the linear momentum of the system? I can calculate that as being G, which is MVC, whose derivative is MAC. So basically that's G dot, which I can calculate as half G dot I. So sometimes it's going to be convenient to use this form, calculate the center of mass, and sometimes it might be just convenient to calculate the sum of MI AI. So that's the balance of linear momentum for this system of particles. Now the balance of angular momentum. I will start with this equation. MHP is equal to Ri minus Rp cross MIVI. Is equal to the sum and I will take its derivative. Oops. H dot P is equal to the derivative of the product is the product of the derivative. No, the derivative of the product is UV, U dot V plus V dot U. Okay. So that's the sum of VI minus VP plus MI VI plus, I'll need to erase this. Did I calculate this derivative correctly? Raise your hand if you're okay with the derivative. If you need more time, take your time. Then raise your hand. Okay. So for the first term here, I can split the sum into two. This will be the sum of VI cross MI VI minus the sum of VP cross MI VI, right? What is this first term equal to? It contains the VI cross VI. There. Now this term here also simplifies. VP, P does not depend on I, and remember I'm summing over I. So P does not depend on I, so I can take VP outside the integral. So I'll be left with VP cross with the sum of MI VI. What is VP cross the sum of MI VI? What is the sum of MI VI? G. So that's VP cross G. Okay. Now here, this term, that is the sum of Ri minus Rp cross MIAI from the balance of linear momentum. This is Fi. Now what is this term equal to? Ri minus Rp cross Fi. What is this term calculating? The moment of what? What is it? MP, which is what? The sum of moments of all the forces about which point? P. Remember? Remember, if I want to calculate the moment of this force about point P, say here, I'll calculate Ri minus Rp cross Fi. And I'm summing that for all the forces, so I'm calculating the moments of all the forces about P. And P, which is the sum of moments acting on the system about point P. So what I get is that H dot P is equal to mp minus vp cross g. And this is the balance of angular momentum for SOP about point P. Any questions? Now I can consider two special cases. If I take P to be the center of mass C, how does this equation simplify? I'll get H dot C is equal to what? MC minus VC cross G. And what is VC cross G? Remember, G is what? MVC. So what is VC cross G? 0. So above the center of mass, the balance of angular momentum is just HC is equal to MC. Another special case, if P is equal to O with VO is equal to 0. So basically, if I calculate the angular momentum about a fixed point O, how does this equation simplify? I'll get that H dot O, again I'm placing P by O where O is a fixed point, is equal to MO minus VO cross G. But what is VO? 0. So I'm left with MO is equal to H dot O. So the balance of angular momentum for a system of particles in general is this, calculated about any point P, moving, doesn't have, moving or fixed. However, about the center of mass, it simplifies, and about a fixed point O, it simplifies to MO is equal to H dot O and P is equal, and MC is equal to H dot C. So what happens usually is that we're solving a lot of problems in class. Sometimes we can, or a lot of times we can use these simplified versions. So sometimes students forget that there exists this version. If you're calculating balance of angular momentum about a moving point that is not the center of mass, then you're going to need to add this extra term. Let us think of an example where you would use this equation. Okay, so consider kind of a cart moving on some rail, and you have a pendulum attached to the cart. If I want to calculate the balance of angular momentum of the pendulum about this point here, which equation do I use? The first, second, or third? So I have a cart that is moving on a certain rail and a pendulum is attached to it. And I have this point here that I called O. It is convenient to calculate the balance of angular momentum of the pendulum about point O, because then the moments of the internal forces at the pin O about O is going to be what? 0, because they're going to pass by O. Exactly. So again, it is convenient for me to calculate the balance of angular momentum of the pendulum about point O to get rid of the moments of the unknown reaction forces at O. But which form do I use here? This form, MO is equal to H dot O. Raise your hand for yes. Raise your hand for no. Discuss. Take a minute, discuss. Exactly. O is not a fixed point. Even though it was confusing and I called it O, I was trying to confuse you. Still, O is not a fixed point. Yeah.
I mean, it doesn't say that the whole time.
Okay, so what do we think? What's the verdict? Can we use MO is equal to H dot O? Raise your hand for no. No. Why not? Is O a fixed point? No. O is not a fixed point. Even though here I tried to confuse you, and I called a moving point O, you still cannot use this equation because here O needs to be a fixed point. So what you'll use, O is not the center of mass either. So you're going to use this equation, and you're going to have to include in your analysis the velocity of this moving pivot O crossed with G. Okay? Does that make sense? Cool. Okay. So where were we at? I removed our plan, but we've done the balance of linear momentum, the balance of angular momentum. We can write their integral forms. The linear impulse linear momentum equation, the angular impulse angular momentum equation. This will be quick. Yeah. Okay, so the linear impulse momentum equation is just that the integral of f dt, f which is the sum of fi, that's one way to write it. So I just take the balance of linear momentum and I integrate it with respect to time. Remember, f is the sum of fi. And we can do the same thing for the angular impulse angular momentum equation. So this form of the balance of angular momentum is not easy to integrate because you have this extra term Vp cross G. But for the other ones about center of mass C, you have the integral of mc dt from T1 to T2 is equal to hc at T2 minus hc at T1. Or about then you can write the integral Okay, so in analogous fashion to what we did for one particle, we're integrating the balance laws to get the impulse momentum forms for a system of particles. Now, for the balance of angular momentum, the one about a moving point P is not easy to integrate because we have this extra term Vp cross G. However, in the other two we don't have it, so we'll stick to the integral forms of the other two, the balance of angular momentum about the center of mass or about a fixed point. What is the last balance law we need to look at before we start solving problems? Work energy theorem. Oy. So the work energy theorem for a system of particles is the sum of the work energy theorem for each individual particle. So for each particle I have at Ti at T2 minus Ti at T1 is equal to the work of Fi from 1 to 2. So that's the work energy theorem for each particle. For this system, I will sum. Okay, where the kinetic energy of the system I can write as T of this system previously defined. Where here, how do I calculate the work of the force Fi? How do I calculate the work of a force between T1 and T2, Fi, acting on particle I? Integral of Fi dot y? V, but the velocity of which point? So now I no longer just have one particle, I have many particles, right? So when I calculate the work of a force Fi, I thought it was the velocity of which point? Its point of application. So the force Fi is being applied at which particle? Mi, which has velocity Vi. So now I need to dot it with the velocity of the point of application of Fi Vi dt. From T1 to T2, which is the integral from of Fi dot dri R1 to R2 or Ri T1 to Ri T2. So now I have to be careful. Velocity or displacement of the point of application of Fi. Okay, very good. So let's do some exercises. Any questions? So, set 14, problem 3. Set 14, problem 3. 3 monkeys, A, B, and C, weighing 20, 25, and 15 pounds respectively, are climbing up and down the rope suspended from D. At the instant considered or represented, A is descending the rope with an acceleration that's given, C is pulling himself up with an acceleration that's given, monkey B is climbing up with a constant speed that's given. Treat the rope and the monkeys as a complete system and calculate the tension T in the rope at D. So take a couple minutes, chat with your neighbor, how do we solve this problem? Okay, so what do we think? How do you calculate the tension force at D? Balance of momentum for which system? For the entire system. So you're gonna take a cut at D, right? So your system is gonna be the 3 monkeys, A, B, and C, with the piece of rope connecting them. So you're gonna calculate the free, you're gonna draw the free body diagram of this, then write the balance of linear momentum, and you're gonna calculate the tension force. So go ahead, do it. And once you're done with this, move on to the next problem, 4. If you have any issues, let me know. You aren't underlining vectors. So again, the monkeys from problems 4-8 are now climbing along the heavy wall, heavy rope wall suspended from the uniform beam. So now the rope is heavy, so it's not massless anymore. If the monkeys A, B, and C have velocities that are given, and accelerations that are given, and the accelerations and velocity directions are given in the graph below, respectively, determine the changes in reactions at D and E caused by the motion and the weight of the monkeys. The support at E makes contact with only one side of the beam at a time. Assume for this analysis that the rope remains rigid, the rope wall remains rigid. Okay, so we want the change in reaction forces at D and E due to the monkeys. So that's why I have two free body diagrams on the wall, one with the monkeys, one without the monkeys, and what we want is the change due to the monkeys. Okay. What kind of reaction force, what kind of support do I have at D? It's a pin. It's a pin. It's not a fixed support, right? It's a pin at D. So what kind of reaction force will I have at D? Yeah, I am going to have a force two directions. So I will have dx and dy. So force D having both x and y components. Okay? Now, due to the monkeys, I'm going to have a D plus a delta D. Here I'm adding the effect of the monkeys, okay? What about at point E? What kind of support do I have at E? Yeah, it's a roller support, so all I have is going to be a vertical force. So that's E, and that's E plus delta E. Okay, so you might be thinking, why is E pointing, the force at E pointing up, not down? Why is it pointing up, not down?
It's a reaction.
Okay, so what?
The weight of the rope is pointing down.
But you can imagine the monkeys like accelerating down, then you would need a reaction force in the opposite direction. So actually the answer is I do not know if E is pointing up or down. I will solve for it. I can solve for it. It can be positive or negative. It will correct itself. The sign will correct itself, okay? So I don't know if the reaction force is going to point this way or in the opposite direction. Okay, then I have the weight of all the beam and the rope. Put it here. Weight of beam and rope. Call it F. Well, weight of beam and rope. And then here with the monkeys, I have the weight of the beam and the rope, plus I have the weight of A, weight of C, weight of B, right? So that's the two systems. Here without the monkeys, here with the monkeys, right? Now, can I calculate D and E without the monkeys? How many unknowns do I have here? If I want to calculate the forces D and E, how many unknowns? So my unknowns are D and E. So how many scalar unknowns is that? 3. So I need 3 equations, 3 scalar equations to calculate these. The first one is going to be the balance of linear momentum. D plus E plus W. You will see that this weight of the rope and the beam is going to cancel out. That's going to be equal to what? Is anything moving in this system? No, it's that. But that's just how many scalar equations? 2. So we need one more, which is, what is? We're going to use the balance of angular momentum, right? The balance of angular momentum, I can choose about which point I can calculate the balance of angular momentum. Which point do you think is the best? Not the best, maybe the most quick, elegant. D, right? Because if I sum the moments about D, I cancel out the moment of this D and I calculate E. So MD, is D a fixed point? Yes, so I can calculate MD is equal to H dot D. What is H dot D here? 0, nothing is moving. what is MD? The moments of all the forces about D. I have to calculate the moment of the weight and the moment of E. So let me call this point F. The moment of the weight is RF minus RD cross the weight, plus the moment of the force E is what? What is the moment of the force E about point D? Okay. So technically, I can now calculate, this is one scalar equation. These three equations are independent. I can solve for the three unknowns if I have the weight of the W. But it will cancel out because I want to calculate the difference here. Okay. Now, I'm going to use the same equations here, but now I have the monkeys. So what is the difference going to be? What is going to change because of the monkeys when I apply these equations? The accelerations are not going to be 0, plus I have to add the weight of the monkeys. So balance of linear momentum, that's going to be D plus delta D plus E plus delta E plus W plus WA plus WB plus WC is equal, now I have to add what? MAC, or the sum of MI AI. And I will notice that since D plus E plus W is equal to 0, I can say that D plus E plus W is equal to 0. So then I can solve for the change delta D and the change delta E. Okay, so that's for the balance of linear momentum. For the balance of angular momentum, I need a bigger board. Okay, now you guys walk me through the balance of angular momentum. What do I do? Right, so MD is equal to H dot D. So how do I calculate MD? Yes, the moments of all the weights. So what is the moment of WA? About point D. RA minus RD crossed with WA, right? Plus what? What is it? RB minus RD cross what? WB plus what? WC plus what? Moment of E, which is what? Plus what? F minus RD cross W. Okay? That's equal to H dot D. And by the way, here I also have a cancellation, which is that the moment of RD minus RE cross E plus the moment of this term, they will cancel out. These are 0. Any questions so far? Yes? Yeah, because this I can expand. RD minus RE cross E plus RF minus RD cross W, and from here they sum to 0. Yeah. Any other questions? Do we all know how to calculate the moment of the forces? So now that I have this expression, all I need to do is geometry, right? I can figure out from the graph, from the given figure, what RA minus RD is. I will cross it with WA. Same for all the other terms. What I still need to calculate is H dot D. Well, first, to be able to calculate the derivative of H dot D, I need to calculate what HD is. So HD is what? The angular momentum of the system about point D, which is the sum of Ri minus Rd plus Mi Vi. So this is going to be equal to the sum of basically Ra minus Rd plus Ma-Va, monkey A, plus Rb minus Rd plus Mb-Vb, plus Rc minus Rd plus Mc-Vc. Now what you want is actually the derivative, so you have to take the derivative of this. So then H dot D will be equal to the sum of Vi minus Vd plus Mi-Vi plus the sum of Ri minus Rd plus Mi-Ai, which the first term simplifies. That's just minus Vd plus the sum of Mi-Vi plus the sum Ri minus Rd plus Mi-Vi. So this is actually what you want to calculate. You will not calculate HD. You will calculate this, H dot D. So you will actually need to use the velocities of all the particles. Well, here, Vd is 0, right? So this term is 0. So this is how you calculate, and here this Ai. So you will not use the velocities of the particles. You will calculate H dot D this way and MD this way, equate them. So plug that back here, equate them, and you should be able to solve for your unknowns, which are now delta D and delta E. So once we have these equations, the rest is geometry and algebra. Any questions? Yes.
In light of the topics we were talking about today, if we recognize that everything acts linearly, can we just condense all the monkeys into one object and then find the center of mass and find all the center of acceleration vectors and then treat that as a system?
Yes, if you're doing balance of momentum and balance of angular momentum, not if you're doing energy.
Oh, okay.
But also might not be the best way or the easiest way to do it, to solve a problem. Yeah. So usually, for example, when you're calculating moments especially, the point of application of the force matters. So if you want to condense all the forces at the center of mass, you're going to have to calculate an equivalent moment too, which you've maybe done in statics. Equivalent force moment systems in statics. Yeah. Okay. So please finish up this problem. Let me know if you have questions. I have office hours today from 1 to 2. And yes, do solve it. And thank you all for coming. Yes.
For the balance of linear momentum without the monkeys, right?
Yeah.
It's equal. D, E, and W are equal to each other because it's not moving.
They sum to 0.
They sum to 0.
Yes, because nothing is moving in the system. The sum of MIAI, if you sum all the particles in the system, they have 0 acceleration.
Oh, okay.
Yeah.
It's like we wouldn't